Hello and welcome to this video on AC theory, looking at resistor and resistor inductor circuits with a short introduction to RC and RLC circuits ahead of my next video. We're going to learn about inductive reactance, phasor diagrams, and we're going to do all sorts of calculations to make you a pro at RL circuits. AC resistor network. For a brief comparison, we'll quickly look at an AC circuit made up of just ohmic resistance from two resistors R1 and R2. They make up the circuit impedance Z as it's an AC supply. We have a 100 volt sinusoidal supply voltage Vs and two voltage drops called VR1 and VR2. In a series circuit there's just one current which we'll call I. We can see the oscilloscope signals Vs, VR2 and VR1 and the current I. Notice that there's no phase difference between them, and this is true at any frequency. AC resistor phasor diagram. The lengths of the vectors for voltages and current represent their amounts in real life, and they're a straight line on the x-axis and there's no phase difference between them. Resistors have no reactance and cause no phase difference between their current and voltage in any circuit. The AC impedance is just the sum of R1 and R2 in ohms. From Ohm's law, current equals voltage divided by impedance and has the units of amps. The voltage drop across R1 is the current times R1, and the voltage drop across R2 is the current times R2. It's independent of frequency. Changing the frequency has no effect on R, Z, V or I. They keep the same amounts and they're always in a straight line on the phasor diagram. The phasor spins anti-clockwise and we can see all the values remain the same no matter what the frequency is, and there's no phase difference ever. Inductor-only circuit. An inductor-only circuit is rarely used at all, but it helps us to understand how inductors work. Here's a schematic diagram of an inductor in an AC circuit, along with some real-life images of inductors. An inductor is simply a length of insulated wire that's been wound into a coil. Inside the coil, there can be nothing, as in air, or a magnetic material. Inductors react to AC, opposing the current flow. Inductors therefore have an amount of reactive ohms, and the amount of reactive ohms depends on the supply frequency. The reactive ohms are known as inductive reactance or XL. There's always a phase difference between an AC supply voltage and the current in an inductor or resistor inductor circuit, and the current lags behind the applied voltage in time and angle, as one period of time for an AC supply is 360 degrees or 2 pi radians. As the supply frequency increases, the inductive reactance XL increases too. From Ohm's law, this means the greater the amount of reactive ohms, the bigger the inductor voltage VL becomes. As the supply frequency increases, the inductive reactance increases. The inductive reactance is equal to 2 pi multiplied by the frequency in Hertz multiplied by the inductance in Henry. If we rearrange the right-hand side of the formula, we can see that there's a positive linear relationship between frequency and inductive reactance. The circuit impedance is just the inductive reactance, as it is the only component in the circuit, assuming it is an ideal inductor with zero resistance and zero capacitance. The circuit current in amps from Ohm's law is volts divided by ohms, which is the supply voltage divided by the impedance or reactance. The voltage drop across the inductor VL using Ohm's law is the current in amps multiplied by the reactance in ohms. Voltage, current and phase in ideal reactive components. Inductors and capacitors oppose AC current, so are said to be reactive components. A really good way to remember the phase difference within reactive components is the word civil. The left side of the word we have sieve. This means that in a capacitor C, the current is in front of the voltage V. Current leads voltage in a capacitor by exactly 90 degrees or 1/4 of a period. On the right hand side of the word we have VIL. And this means that in an inductor, L, the voltage V is in front of the current I. So current lags voltage in an inductor by exactly 90 degrees or 1/4 of a period. Phase difference is defined as how much the current leads in front of or lags behind the applied voltage. For an inductor-only circuit, the supply voltage and the inductor voltage are the same. In series circuits, as components share a common current, we use current as the reference vector on the x-axis. And the x-axis is the position that sine waves start their cycle on the phasor, spinning anti-clockwise. With the inductor current on the x-axis, the voltage across the inductor leads by 90 degrees. This means the inductor voltage sine wave is at its positive peak or maximum value when the inductor current crosses the x-axis and begins to increase from its starting value of 0 amps. Let's use an analogy to help remember this. I mentioned ideal or pure components, and this just means that an inductor only has inductance and no resistance or capacitance, but in reality, all components have some resistance, some capacitance, and some inductance, although the unwanted amounts are usually small and can be ignored. Imagine that the inductor voltage VL and the inductor current IL are having a race on a running track. VL and IL always run at the same speed, so they have the same frequency and angular velocity. They're always 1/4 of a lap apart, no matter how fast they run, and the current lags behind the voltage. If we decided to put a capacitor in series with the inductor, then from the sieve part of the civil wood, the current would lead the capacitor voltage by 90 degrees. The two reactive voltages are 180 degrees out of phase with each other, or half a lap, no matter how fast they run. And as they all run faster or slower, the only difference on this diagram would be the amounts of voltage and current. The phase difference would remain the same. Here's a phasor diagram for a series inductor-capacitor circuit. They share a common current, and the reactive voltages are always out of phase with each other by 180 degrees. The length of the voltage vectors depend on the current and capacitive and inductive reactances, which depend on the frequency. Here's a series RLC circuit, which is very common. Current is a reference vector in a series circuit, and the phasor is similar to the LC phasor, but we now add the resistor voltage vector. Resistor current and voltage are in phase in any circuit. VL leads the current and VC lags the current. The supply voltage position depends on whether VL or VC is greater, which depends on the two reactances at the given frequency. In this example, inductance is dominant, so VL is larger than VC, and the circuit current is lagging VS, with VS above the x-axis. If the capacitive reactance was dominant, VC would be dominant, and then the current would be leading VS, and VS would be below the x-axis. The phase angle is shown on the phasor and on the running track. And here's the short animation with everything to scale. Series RL networks. Firstly, at a lower frequency. Let's look at the series RL phasor diagram, knowing that phasors spin anti-clockwise. Vs is the supply voltage and is the hypotenuse of a right-angled triangle. The supply voltage vector Vs is a constant length or amplitude regardless of the frequency, unless we physically change the voltage on our signal generator. The resistor voltage VR is the adjacent side of the right-angled triangle and starts on the x-axis. The length of the VR vector does change as the supply frequency changes, depending on how much voltage is across the resistor. The inductor voltage VL is the opposite side of the right-angled triangle and starts on the y-axis. The length of the VL vector does change as the supply frequency changes, depending on how much voltage is across the inductor. We can use Pythagoras' theorem to work out any of the voltages if we know the other two. For example, the supply voltage is equal to the square root of VR squared plus VL squared. We can use simple trigonometry to work out the phase angle if we know any two voltages. For example, if we know Vs and VR, the hypotenuse and the adjacent side, we use inverse cosine to find the phase angle. The phase angle is between the supply voltage and the current, and in a series circuit, it's also the angle between VR and Vs, as VR is in phase with the current, and current always lags the supply voltage in an inductor or resistor inductor circuit. Firstly, let's have a look at the voltages at the relatively lower frequency of 300 Hz. The inductive reactance XL will be lower at a lower frequency. Ohm's law shows that the inductor voltage VL will be lower too, therefore the resistor will have more voltage across it. This makes for a shorter triangle, therefore the phase angle is lower at low frequencies. This animation shows the rotating phasor and the voltage waveforms as time passes. The frequency is 300 Hz, which is my lower frequency, so the phasor would spin 300 times per second in real time. At a lower frequency, the resistor has a larger share of the supply voltage Vs. This is due to the lower inductive reactance of the inductor, causing a smaller inductor voltage. Current always lags the supply voltage in an inductive circuit. The resistor current is always in phase with the resistor voltage in any circuit, so we can use Vs and VR here to see the time difference between the peaks. Series RL network. Now we're going to look at a higher frequency. Let's look at the voltages at a higher frequency of 1 kHz. The inductive reactance XL will be higher at a higher frequency. Ohm's law shows that the inductor voltage VL will be higher too, so therefore the resistor will have less voltage across it. This makes for a taller triangle, therefore the phase angle is greater at high frequencies. Let's compare the phasor and waveforms at 1 kHz, which is my chosen higher frequency. At a higher frequency, the resistor has a smaller share of the supply voltage Vs. This is due to the higher inductive reactance of the inductor, causing a larger inductor voltage. At 1 kHz, the time difference between the peaks of Vs and VR is noticeably larger than at 300 Hz. This means that there's a greater phase difference at the higher frequency. How change in frequency impacts our formulas. Here's the RL circuit schematic diagram along with the voltage triangle and impedance triangle. At any frequency, the two triangles are technically similar in that they have the same internal angles. As we lower the frequency of the supply voltage on our signal generator, this reduces the inductive reactance. The knock-on effect is that the circuit impedance Z reduces slightly, and less impedance means more current, I. The reduction in reactance reduces the inductor voltage. As we increase the frequency of Vs on our SIG-gen, this increases the inductive reactance. The circuit impedance increases slightly, and more impedance means less current. The increase in reactance increases the inductor voltage. How change in frequency impacts waveforms. For all examples in this video, the supply voltage Vs has a 100 volt amplitude or peak value. These are the lower frequency waveforms. We see the current lagging as it does at any frequency in an inductive circuit. The inductor voltage has a relatively smaller amplitude, and the resistor voltage has a relatively larger amplitude. At 300 Hz with our component values, the delay between Vs and the current is around 9% of one full cycle, and this relates to a phase difference of around 32 degrees. And to work these out, see the link to my video called Measuring Phase Angle Accurately with Multisim Life. These are the higher frequency waveforms. The inductor voltage has increased and the resistor voltage has decreased. At the higher frequency of 1000 Hz with our component values, the delay between Vs and current has doubled to around 18% of one full cycle, and the phase difference has therefore doubled to around 64 degrees. With a high frequency and/or a large inductor, XL is high, therefore VL is high, so the resistor has less voltage dropped across it. The phase angle is high. With a medium frequency and/or a medium inductor value, the inductive reactance is reduced, so the voltage across the inductor is reduced, so there's more voltage for the resistor. We have a medium phase angle. Then at low frequency or with a small inductor value, XL is low, therefore the voltage across the inductor is low, so there's more voltage left for the resistor, and the phase angle is low. This is just a summary which you can pause on or screenshot if you want to. So series RL calculations at the lower frequency. Firstly, we need to find the inductive reactance, which is equal to 2 pi FL, which is equal to 2 pi times 300 Hz times 0.33 Henry. So XL is 622.035 ohms. And now we can find the circuit impedance Z. And that's equal to the square root of the adjacent side squared plus the opposite side squared in terms of ohms, which is the square root of 1000 ohms squared plus 622.035 ohms squared. So the full circuit impedance Z is 1177 ohms roughly. Now we can find the circuit current, which is voltage divided by impedance. So that's 100 volts divided by the Z value. So the series current is equal to 84.91 milliamps. Now we know the current, we can find the voltages. So the resistor voltage is current times resistance from Ohm's law. So that's I times 1000 ohms. So the resistor voltage is 84.91 volts. Now the inductor voltage, VL, is equal to the current times XL. So that's 84.91 milliamps times roughly 622 ohms. So the inductor voltage comes out as 52.819 volts. Remember, the supply voltage amplitude or peak value is not equal to the sum of the resistor peak voltage and the inductor peak voltage because the peaks occur at different times. The resistor and inductor voltages at any instant in time, though, do add up to the supply voltage at that time. This means the y-axis components of VR and VL do add up to the y-axis component of VS at all times. And remember, sine waves spend very little time at their peak values as they're constantly changing. Now to the phase difference. There's the voltage and impedance triangles. As we know all three sides of the impedance triangle and all three sides of the voltage triangle, we can use inverse sine, inverse cos or inverse tan to find the phase difference using either triangle. But it's common to use the inverse tan or shift tan function on our calculators with XL as the opposite side and R as the adjacent side. But we could use inverse tan of VL over VR if we wished, and we'd get the same answer for the phase angle. Either way, the phase angle is equal to 31.88 degrees at the lower frequency of 300 Hz. Let's do the same calculations at 1 kHz. First we need to find the inductive reactance, XL. That comes out at just over 2 kilo ohms, 2073.45 ohms. Now we can find the circuit impedance, which is the mixture of resistance and inductive reactance. So the impedance of this circuit is 2302 ohms. Now we know the impedance, we can find the current using Ohm's law, Vs over Z. That's 100 volts divided by 2302 ohms. So now at higher frequency the series current comes out as 43.44 milliamps, so it's a lot less. The resistor voltage is I times R. And the resistor voltage will come out as 43.44 volts. The inductor voltage is the current times the inductive reactance. So the inductor voltage will come out as 90.07 volts, which has gone up quite a lot. Let's find the phase angle at the higher frequency of 1000 Hz using either the impedance triangle in ohms or the voltage triangle in volts. Either way, the phase angle is equal to 64.25 degrees, which is a lot more than it was at 300 Hz. Let's summarise by seeing how the measurements have changed by increasing just the supply frequency. The inductive reactance is increased by the same percentage that the frequency increased. The impedance increased, but by a smaller percentage due to Pythagoras' theorem. The current is reduced by the same percentage that the impedance increased. The resistor voltage is reduced by the same ratio that the current reduced from Ohm's law. The inductor voltage is increased by its own ratio that depends on the impedance and reactance. Finally, the phase angle has increased significantly at the higher frequency. This image will help you revise and remember the basics if you want to print it out or screenshot it. Please like and subscribe, ask me lots of questions, and thanks so much for watching. All the best from me, James. Cheers.